Hello everyone, I'm Mojtaba and welcome to another episode of A Sip of Chemistry. So far, I've had the opportunity to speak with wonderful scientists from around the world. Today, I'm excited to introduce Professor Sharon Ashbrook, a renowned chemist and leading expert in solid-state NMR, currently at the University of St. Andrews. Her journey began with a chemistry degree at Hertford College, Oxford, where she developed a passion for NMR research, particularly in quadrupolar nuclei. After postdoctoral work and a teaching position at Cambridge, she moved to St. Andrews, where she has continued to innovate in NMR techniques and applied them to a wide range of disordered materials, including glasses, electrodes, and zeolites. Her favorite nucleus is oxygen-17, and her recent research has significantly advanced our understanding of this challenging isotope. With over 100 published papers and prestigious awards including Corday-Morgan Prize and the Bourke-Liversidge Award, she also dedicates time to outreach, inspiring the scientists uh, through her roles with the Royal Society of Chemistry and the Royal Society of Edinburgh. In 2019, she was recognized as one of the outstanding women in science by the Royal Society of Edinburgh. Please stay tuned and enjoy my interview with Professor Sharon Ashbrook. Thank you so much, Professor. Thanks for agreeing doing this interview. Uh, at the beginning, just like always, I would love to learn about your education. Where did you get your degrees?
So I guess I grew up in the northwest of England, and so I went to school there, and I went to university at the University of Oxford. So I did my undergraduate degree, which was an M.Chem, so a 4-year degree, at Hertford College in Oxford. Graduated around 1997, I think it was. And then I'd always wanted to be a primary school teacher, so that was what I decided I was going to do. But in the last year of my degree, I did a research project, and that was with Steve Wimpress on NMR spectroscopy of solids. And I really enjoyed that. And so I was persuaded to do a PhD, a DPhil in Oxford. So I stayed there and did another 4 years there, graduating in 2001, I think. Then I worked for a couple of years as a postdoc at the University of Exeter before I had a fellowship, an independent fellowship at the University of Cambridge, actually in earth sciences rather than in chemistry for a few years. And I came to St Andrews in 2005, I think it was.
Okay, then you started your career as a chemistry professor.
Yep, that was my first independent job, yeah.
Yeah. So, why did you choose chemistry when you wanted to come to the University of Oxford?
I'm not very sure because when I was at school, my favourite subject was geography, and my best subject by a long way was maths. But I think I had a really, really inspirational chemistry teacher. And certainly towards the end of school, I got really interested in what they were telling me. And they were really supportive and probably started me thinking about whether science was something that I could do and whether I should think about that moving forwards. And I think when I applied to university, I was still contemplating maths a little bit, but I wasn't really sure what a maths degree at university looked like. I wasn't sure what it did apart from just more maths. Whereas for chemistry, my teachers had told me about all these really interesting areas that you just can't look at high school, a lot of practicals that you could do, things that were really different. And that sounded a bit more interesting, a bit more exciting. And I also thought maybe there'd be a wider field of jobs, maybe from a chemistry degree than a maths degree. So I applied for chemistry. I think what I found during my chemistry degree was that I really liked the theory of organic chemistry. I was the best at organic chemistry by a long way, but I hated the practicals, just hated practical chemistry. I found physical chemistry a lot harder, a lot tougher. But I really like the kind of logic and problem solving behind things like spectroscopy. And so I think that was why I chose to do my project in that area in the final year of my degree. And that really changed, I guess, what I then went on to do. So yeah, I'm not really sure when I made the decision for chemistry. I think it was probably a decision not to do maths, probably, rather than a decision to do chemistry.
What do you do at your research lab?
So my group combines experimental NMR and first principles calculations, so DFT calculations usually, and our aims to try and understand local structure, disorder, and chemical reactivity, mostly in inorganic materials. So my PhD, my expertise was in method development for quadrupolar nuclei. So I still have quite an interest, obviously, in trying to look at as many quadrupolar nuclei in a system as I can. But the work that we do uses probably a kind of multi-nuclear approach, as many elements as we need. We do quite a bit of work on porous solids, so materials that have kind of pores and channels that are similar sizes to small molecules. And so this leads to applications in things like catalysis and drug delivery, gas storage and separation, that sort of thing. And they can be really difficult to characterize. So NMR comes in really useful there. We're quite interested in disorder. We look a lot at compositional disorder, how when you mix atoms and nuclei in a material, how that changes the physical and chemical properties. And of course, NMR is ideal for kind of looking at how atoms are distributed within a material. So I guess over the years, we've worked on lots of systems, minerals maybe from the inner earth we do a lot of work on. We've worked on ceramics for waste encapsulation. Current work, we're looking at a lot of industrial catalysts, not really published too much on that yet. And maybe some new projects as well on battery materials. I guess the only other thing maybe that we use a lot of isotopic enrichment in the work that we do. And this obviously helps us with our sensitivity, but also it offers us a really good opportunity to get more information. So when you use an isotopically enriched reagent in a synthesis or in a reaction, you can kind of look and see where that isotope goes in that reaction, where it's incorporated into material, how it moves around through the reaction. And that gives you a lot more information that you can't really get from other techniques. So yeah, combination of experiment, DFT, isotopic enrichment to look mainly at inorganic materials.
Yeah, you are covering a wide range of materials, right? And what's the main common things between them? You know, you talked about the catalyst, lithium-ion batteries. So it seems that they looks different. But what's the common things between them that actually you are interested in them?
So I think that's a really interesting question, actually. I think most of those materials are disordered in some way. And so diffraction either struggles or gives information on an average structure, a structure that's averaged over time and space. And so spectroscopy can really provide that sort of atomic level detail to really work out what's going on. We work on materials that are often brought to us by collaborators, by other people, problems that they're trying to solve. So sometimes they're not very related at all. But for me, I think the key challenge is always what experiments I can design, what computation I can do that would try and answer those questions about that atomic level detail. So what can NMR actually tell us about a particular material? So I think mainly linked through disorder, often through oxygen NMR, which is one of my favorite nuclei, but not always. So I think, yeah, it's a mix of things we drive and things that collaborators bring to us, I think.
Yeah, you mentioned about the oxygen 17 NMR. I think it's a tough isotope to work on it, right? How has your research advanced our learning of oxygen NMR?
That's a tough one. So I've always been interested in oxygen. It was one of the very first things I did in my PhD, actually. I did a lot of method development, but the first collaboration I had as a PhD student was with some earth scientists who wanted to understand whether oxygen NMR could tell them how the minerals that are in the inner earth store water, how you could find out where those hydrogens and that water was. And that led to a collaboration that's lasted sort of 20 years, all the way through my postdoc and my independent career. Oxygen's often, I mean, it's in most of the inorganic materials that we look at. So, of course, it offers us if we can develop methods to study it well, it offers us lots and lots of information. I mean, the natural abundance of oxygen is obviously a challenge. So it's 0.038% abundant. So that is a real problem for sensitivity. But I think really what's interesting is what I said earlier is if you can isotopically enrich, you can improve that sensitivity, but you can also get a lot of information. And so you can then follow how reactions and syntheses happen. I think what has our work really achieved? I think we have contributed quite a bit to different methods to enrich materials, particularly porous materials. We've introduced quite a lot of new methods, synthetic methods for that, improved and optimized some of the existing methods. And of course, we now have a lot of experience with high resolution NMR, sensitivity enhancement techniques. But I think the main contribution has been in understanding the materials themselves. So contributions to earth sciences, to engineering, to catalysis, to really understand how a material works, mainly by using oxygen NMR, but often with other nuclei as well.
As an expert in solid-state NMR spectroscopy on oxygen 17, if you receive an article for review, so which types of mistakes, if you see, you actually reject the article, or what you have seen in the literature as the most common problems when researchers try to work on this nucleus?
So obviously most of the papers I get to review are fantastic, and often I'm just quite jealous that I didn't get to write them. I think most of the things that you see in a paper when you read it first as a referee, most of the sort of inconsistencies or the things that are unclear, you can usually iron most of those out in a referee's report. So you write back, the author makes some changes, sometimes does a few experiments. But I think the papers that I have rejected have actually, one of the most common mistakes for people who aren't NMR spectroscopists is to take the second order quadrupolar line shape, so this complex line shape that you see for oxygen or for all quadrupolar nuclei, and to start fitting it as multiple Gaussians, and then to try and understand that in terms of multiple chemical sites, which of course is really not the case. And I think in those cases, when people have got clearly less expertise, you try and point them to the right places, how to do those experiments. But sometimes that doesn't really work. They don't really listen. And so I think in those cases, I probably have rejected papers. I guess don't reject that many papers. I maybe shouldn't say that out loud, but mostly you can work, the whole point of a referee is to try and improve a paper, not to stop it being published. But I think if something's fundamentally wrong, if it's inaccurate and it's going to lead to other people having misconceptions, that's probably where I would reject something.
So have you ever received an article, I mean, for review, for peer review, and you say, so this is a big mistake, or this is not a mistake, this is something that we have worked on it and we found different results. I need to discuss it, or I need to contact these authors. Have you ever had this experience?
I think probably not directly, probably not so similar a material or so similar a system that it's you can be very confident that your material is identical. I think within organic materials, because of the way that they're different when you synthesize them, small changes in synthetic conditions can make quite a bit of a difference to things. I think sometimes you have a suspicion something maybe hasn't been looked at carefully enough, or but it's difficult sometimes to prove that, I think. So I would always offer advice. I would always point people to papers where I think either my work or somebody else's work has said something different. And kind of, I mean, what I really like about a good paper is not just presenting results, but also explaining what you don't know. So, what's a certain conclusion? What are you fairly sure about, and what's a bit more speculative? I really like understanding the errors and the uncertainties that are in people's work. And I think if you can compare to something else and say why you think yours is different, then time will tell eventually which one of two people perhaps are right, or whether they really do have different materials. So I don't think I've ever really found myself in the position where I felt I had really to contact someone or it's been too close. Um, I think more usually, maybe going back a little bit to your previous question, I think for oxygen and for quadrupoles, people often integrate spectra in a way that you can't do unless you've taken a lot of precautions. So precautions with short flip angles, nutation rates, and particularly if you've got small CQs, you need to account for the satellite transitions underneath your signal. And that's often something that people don't do. So I think in that case, I obviously in a referee's report would write a little bit more advice or help on that and hope that that could be fixed or changed.
Okay, just in order to clarify my last question about uh, the, uh, the results that you see in the literature, I wanted to, I meant that it's not a mistake. It's something that you have worked on it. You have different opinion. You know, my point is that I've not seen in the literature quite often the discussion between researchers. You know, so does it mean that you publish something? You generally, I mean, you as a researcher, you publish something and you let the readers think about it and decide if it's valid or not. Uh, I mean, if you believe that something that's published is misleading, don't you think that you need to actually just uh, discuss it, just as a comment, something like that? Yeah, the reason that I'm asking again this question is that I don't see these discussions that might be helpful for advancing the research and the science, isn't it?
Yeah, it's an interesting question, isn't it? I mean, I don't think I've really found myself in that position. And when I have, it's been more at conferences. You know, somebody's given a talk at a conference, and then it's easy because you've got the option afterwards to go up and to talk to that person. And actually, once or twice, we've ended up combining results or publishing together on something. Um, really think I've ever found that in the literature, but I think, as I said, if you provide your information on how certain you are about things, you provide open data. I'm a big fan of publishing the data, then people can take that data and they can do different things with it. And you know, I'm always prepared that, particularly in a couple of years' time, somebody will come along with new ideas or new techniques or new instrumentation, and they'll prove something that you did was either not the whole story, or maybe sometimes incorrect. But I think as long as it's the best you can do at the time and you say what your evidence was, I think that's good. I don't think I've ever really come across something that's really been so obvious that I've felt that I needed to write a comment or to do something. But I think I probably would if it was necessary. I mean, you'd have to contact the person first, maybe, and try and see what they were thinking, or maybe they've got evidence you don't know about, I guess. But it's an interesting question why we don't see more of that maybe in the literature.
Yeah. In your opinion, how DNP, dynamic nuclear polarization, can facilitate measuring oxygen NMR, oxygen 17 NMR without enriching?
So I've worked on DMP a little bit during my career, but we don't have routine access to it here in Scotland, and we have a national facility, but it is pretty expensive to access, particularly for PhD students who don't really have research grants. So the work that I've done on DMP has often been through collaboration. Now, obviously, DMP offers massive sensitivity enhancements in principle. And so particularly for something with low natural abundance like oxygen, there are going to be many systems where it might truly transform what you can do, particularly in systems where you can't enrich something or where that's going to change the material that you're looking at. But you've always got to be a bit wary, I think, about anything you do to a system, whether it's enriching it or whether it's adding your polarizing agent and your solution, because certainly for some of the systems we looked at, the DMP itself changes the material and goes a phase transition or different surface structure. So I think I would always advocate trying to combine techniques. You always need the most information that you can. So I don't think even if I had DMP, I would completely stop enriching things. I think you would be able to enrich selectively. You'd be able to really exploit that real sensitivity that DMP gives you by combining chemical techniques, NMR techniques, and DMP. So that was probably a pretty terrible answer, actually. But I would do all of it, I think is my answer.
Yeah, I guess my next question is about the DFT. You mentioned that you actually do DFT calculation. How does DFT help you to understand the results of NMR better? So it's for me, I don't know that much about the computational chemistry. For me, it's just like the egg and chicken problem. Which one comes first? You should have the NMR results, then build up a DFT calculation, then then justify your NMR results, or no, you do the DFT calculation independently. So how does it work?
So I think that's a really excellent question. I think when we first started doing DFT calculations, we started pretty early on through a really early collaboration. I think we were always doing them to explain a spectrum. So we had a result and we wanted to assign signals. We wanted to know what happened if, you added a titanium, did it move this way or this way? And so the focus was very much on the spectrum, I think, with the DFT kind of supporting that. I think the work that we do now on disordered materials is a bit more 50-50 actually, and probably those two things go on simultaneously. So if you've got a material that you really don't know much about the structure for, you've maybe got a diffraction pattern, or maybe you know the framework, but you don't know where all the atoms are, then DFT can really help you narrow down which ones of those structural models are possible. So you can calculate lots and lots of different models. You can work out which ones have low energy, which ones have high energy, and you can really focus down on trying to understand which ones are feasible. You can predict NMR parameters, predict a spectrum, and then go compare to your experimental results. So I think the way we use DFT depends on the problem, depends on what we know already about the material, but probably alongside experiment, with the idea being that together, combining them, you get that structural insight, which is really difficult otherwise. So I think we probably do them simultaneously. Maybe depends how long they are and also how complicated the experiments are. I think if you can predict something with a DFT calculation, you can speed up an experiment. You can know, particularly for nuclei that you've not looked at very often, you know where to look in a wide spectral range, put your transmitter in the right place. If you know you've got a very, very large quadrupole, you can change the way you're going to do the experiment, for example. So I think it can also be useful to do them first and to try and guide the experiments for things that you're really less confident at, I guess. So all of those things, before, during, and after, I think we would do.
You briefly mentioned about the application of NMR in characterizing disordered materials. So why NMR can do it best when it comes to comparing the characterization techniques? So how NMR is the best candidate for studying these materials?
So I guess disordered materials, it depends. I mean, there's so many different types of disorder. You can have compositional disorder where you vary the atom, but it stays in the same place, but you vary the type of it. You can have positional disorder where the position of an atom moves around. And you can have dynamic disorder, so where things are moving in space. And of course, depending on what your system is, what type of disorder you have, different techniques treat or result, give different results for those. So diffraction, as I think I said earlier, gives you an average structure. And, if you get an average structure from diffraction and you know that an atom is there 50%, is that 50% of the time and it's somewhere else? Or is it 50% of the material has an atom there? And of course, spectroscopy, because it looks as that local structure, can really tell you about the atoms that surround things. We know that NMR is also super sensitive to motion on 15 orders of magnitude timescales. So I think local structure, local information is really key when you're looking at disorder. But I think it's really useful, and one of the things computation helps us do is bring in that diffraction information. So a technique called NMR crystallography, where we combine information from diffraction and order with the NMR local structure. And the computation kind of bridges the gap there. It allows us to kind of combine those two. So I think for disorder, it is just the fact that NMR is a local probe and therefore doesn't need that long range order. We can apply it to polymers, to glasses, to gels, to ceramics, as well as to ordered crystalline solids.
I have a general question about the way that you have learned from your mistakes. I'm a person that I learn from the mistakes that I've done in the lab. How sometimes it's been a big mistake, sometimes it's costly. So how about you? Can you give us an example of mistakes, something that you didn't do properly, and you learned something from that, and that was a good experience for you for advancing your career?
I mean, I make a lot of mistakes as well. I think everybody does. Some are small, some perhaps a little bit bigger. I think you learn something from every mistake that you make, even if it's something simple like read the paper a little bit more carefully, or remember to check the power before you leave the lab, so you're not doing a pulse with no power. Do that quite a lot. Difficult to think of a mistake that's really changed things, that's really led to something different or something new. I think there's been lots of times in my career where luck has led to something different or something new, but struggling to really think about whether that's a mistake. Yeah, probably not. Just more. I don't think they've ever been big enough to change things, to make a different research direction or bring out something completely different, but certainly saved a lot of time when we've worked out how to do things. Wasted a lot of time. I've certainly pulsed for 3 or 4 days without a sample in the magnet a couple of times. For nuclei like oxygen, where you're not expecting to see a signal, it's not immediately obvious that things are going wrong, so you can waste a lot of time that way. So that's probably a pretty terrible answer, but more luck than mistakes, I would have thought, for my research and my career.
In your opinion, what makes a researcher a good scientist? Is it all about the novelty and the way someone thinks, or that's the facility? I mean, if you have expensive facility in your lab, you can do impressive stuff, research work, or how do you see it?
I guess it's both of those things, isn't it? In that you have to have some knowledge, you have to have some skills to be able to do a lot of the research that we do. But I think the ability to think of new things, or to take a risk, or to do something different can really take you in a different direction. It can open up areas or things that would have been missed, I think, otherwise. And that's probably something I'm probably not as good as probably some of my students and postdocs, who are much more likely to try things. I'm quite safe. I like things that I know are going to work and aren't going to blow up. I think I would also add in a couple of different qualities, though. I think one thing is really important to have is, I think it's important to be able to work hard. Research is really difficult, and there are times when things don't go well. And I think having that ability to work through something, to have patience, perseverance, to really push through the tough times and the tough problems, I think that's really important. And I think the thing I really like hearing about in my group, or I like hearing that people in my group have, is the ability to spot something that's weird, to kind of look at something and say, that's a bit odd. I wonder what would happen if I did this. And I don't really think of that as novelty in a sense because you're not designing it to be new, but spotting when something isn't what you expected. I kind of feel if you're pushing on towards an end goal and you're the only thing you want to do is get that one spectrum, that one figure, that one thing, you tend to miss some of the things that don't quite match what it is that you wanted. And I think being able to spot that, think about it, investigate it. So watching the spectra as they come in sometimes, rather than processing them 4 days later when you've not got the ability to test something, or when you're analysing something, looking at the bits that don't quite match with what you wanted. So I don't know what the word is for that ability, but I think that is probably key to really solving the problems and really taking problems in a new direction. So novelty is great, but I think being able to spot novelty is also quite important.
Yeah, that's interesting. In 2019, you were elected as one of the women, outstanding women in science, elected by Scotland's National Academy. I guess that's the true name, Scotland's National Academy. So, how do you feel about it?
Well, I was really surprised, obviously, to be selected. I think there's about 25, 26 women across Scotland in all branches of science that were selected to be part of the Royal Society of Edinburgh, the RSE Women in Science exhibition. And this involved a big photographic exhibition. We all had our portraits taken. I've never had 2.5 hours of makeup before in my life, which was quite interesting. And that exhibition was at the RSE in Edinburgh that people could go and visit for about a year, I think. But then it went on tour around Scotland. So it was at places like the airports and the train stations, the libraries, museums, and the public buildings. And it really generated quite a lot of interest. So each of us had our portrait, a little bit about our background and the research that we did. And we all had to carry an object that we thought represented the science that we did. And I think what I really liked about the exhibition when I saw it out touring around Scotland, was that one of the frames looked like it was bare, it looked like it was blank. But when you stood in front of it, you realized it was a mirror. And the idea was that it would show younger girls, young females, that they could also be in this exhibition in the future, that they could see themselves there. So it was a really cool thing to be part of. It was slightly less cool to see yourself at Edinburgh Airport when you were waiting for a plane, and that led to some slightly weird conversations that it's a little bit weird. I also had a really good opportunity, I think it was last year. Princess Anne visited the Royal Society of Edinburgh, the King's sister, and I got chosen to present this exhibition to her and to show her what the aims were and what the success had been. And although I was really, really nervous, she was really, really nice. She asked lots and lots of very interesting questions. So that was a really good experience as well. So yeah, it was a great experience to be part of, I think.
My next question is the discrimination against women in science. So, we are in the 21st century, and we still, I think, we have it. So, first of all, why do you think it happens?
Well, I think if I had the answer to that one, I would probably be able to solve a lot of problems. I think things change very slowly, and I think that a lot of what we see in science now in the 21st century actually reflects what happened or what society was like when I was younger or when my parents were younger. Um, and certainly when I was at school, it was unusual for a girl to want to do science. I think by not having women in science, particularly at the highest levels, then there's an expectation often that women look after children, women take notes, women look after the house, women don't go out to work as much. And that, although it's a very older view, of course, it takes a long, long time for society to change and for people to get through to the kind of management level of jobs. So I know when I was a kid, my expectation was always that I would have a job, I would be a primary school teacher. Um, But when I had a family, I would stop having a job because that was what all my friends, all my family, all the people I knew did. That's a slightly different question. That's why there aren't more women in science. It's a slightly different question to why women do experience discrimination. And, they do from simple things like, I said I'm often the only female in a room at a meeting, and it's often assumed that I'll take the notes, even though I'm often the most senior person there. And it's not a big thing, but it's kind of inherent in society in the way that people kind of just expect women to take those sorts of roles on. And I've had a couple of bad experiences on panels, grant panels and fellowship panels, where I think I have really been treated differently to my male colleagues, where my opinion's either ignored or I do remember once one very bad experience at a grant panel down south where I'd expressed a negative view about a candidate, and an older retired male professor told me that the science involved was very complicated and I probably just didn't understand it. And that was about 4 or 5 years ago. And I just don't think people would say that to a male colleague in the same way. So why it happens is a trickier question. But yeah, I've certainly experienced it, I guess, in my career.
Okay. Thanks for your insight and comments about this problem. So just a quick follow-up question. What is your expectation as a women in science? Expectation from the whole community, the whole science community. What's your expectation as a woman in science to remove these discrimination?
I think one of the things that strikes me is that I spend a lot of time on panels, on committees and on boards, on recruitment panels, fellowship panels, because all panels need to be gender balanced or gender diverse. And that's a really good aim. And I think that's true. But of course, there are far fewer females to fill those roles. And so I spend a lot of time doing that. And this, of course, limits the amount of time that I can spend on science. And it's something that, you always have to weigh up whether it's a good use of your time or whether you should be doing more science. And I think a couple of years ago, I really came to a decision that I thought, although it was going to take a lot of time, I would put effort into committees and panels, probably more than I should, to make sure that there is a diverse view, to make sure that you really can try and address those biases as they're said in a room, and to try and just give the younger females maybe coming behind me in a career, hopefully a slightly better experience maybe than I've had. I kind of feel it's easy to moan about change. It's easy to moan that change doesn't happen. So you really have to get out there and actually actively make that change. I've also often done a lot of outreach work. I do a lot of work with local schools, and I think that is really important for people really early in their career when they're thinking about science, to see that science is a thing that females can do, to have those female role models. And one thing I did a couple of years ago with 2 colleagues here in St Andrews, we wrote a couple of booklets looking at the academic careers of women in Scotland, where they'd come from, what their career was like, what their pathway was like. And I think that was a really interesting experience. We published 2 of these books. And what I think it brought home to me was that there's very, very many different ways to get into academia and to be in academia, and that you don't have to have this very standardized career pathway. People had taken lots of career breaks. Some people had moved abroad, some people hadn't. It was a very, very different picture. And maybe it's time for a bit of that in NMR as well. Maybe we need to have a look at what sort of careers people have, what we value maybe in science. So I think good role models, and I think you have to proactively do something. I think you have to make a change. And for me, that's giving up time, I think is probably the easiest way that I can contribute, but certainly something I feel pretty strongly about.
For the last question, I'd like to ask about the conferences. So you are the co-chair of the ENC ISMAR. I don't know how you pronounce it, this acronym. Is that true? ENC SMAR conference. So would you tell us about the history of this conference?
Yeah, so the ENC runs every year. It's the American Experimental NMR Conference. It's always held in America, often on the east and west coast. It often alternates. But when it's on the west coast, it's often in Asilomar, so a state park in California. And next year, the ENC is going to join up with ISMAR, the International Magnetic Resonance Conference that travels around the world. We're going to bring together those two fairly diverse bodies, actually. So it's a really great opportunity, a really interesting conference. Has the potential to be quite a different conference, quite a large conference, but it's going to be really exciting, I think, to be in charge of that. Asilomar is a really unique place for a conference. It was actually the first international conference I went to. And I was slightly disappointed when I went to other conferences to realize that they all weren't on the beach in California with free food and drink and vendor suites and lots of free things. It was a really different opportunity, a really different experience for my first conference. So I think, yeah, the ENC ISMAR is going to be a very different conference, but it's a great venue, and hopefully it'll be a really good scientific meeting. So we're just choosing our invited speakers now. So we're just inviting those at the moment.
Okay, amazing. So I would like to go to the next part at Beyond the Lab. And usually I ask the same questions from the professors, researchers, the science community. What do you do at your spare time?
I think my biggest interest outside of science is probably football. I'm a massive football supporter. So a lifelong supporter of Liverpool FC. So that's the town where I was born. So I watch quite a lot of football. Sadly, not too many live games nowadays. So mostly on the television. I like most sports. So I used to be an elite gymnast when I was younger. So I watch quite a lot of gymnastics as well. I keep up with that. I think more generally, I like reading crime fiction. Also quite like history. I read quite a lot of history, watch quite a lot of historical documentaries, and recently, last few years, I've really helped my mum trace her family history. So I've got quite interested in genealogy as well. But apart from that, I like going out to dinner and drinks with friends and just the kind of normal social stuff, really. But yeah, maybe sport probably is my biggest interest.
So I think you mentioned about your dream job when you were a kid, right?
Yeah, so
You wanted to be a school teacher?
yeah, I want to be a primary school teacher, so to teach really little kids. My parents were both primary school teachers, so I'm not particularly inspirational. And that's all I ever wanted to do. I used to play school when I was a kid, used to line all my toys up and play school. And that was always really my aim. So I wanted to get a degree. My parents encouraged me to get a degree. But I always had that aim of teaching afterwards. And it was really when I enjoyed my research project that I decided to do a PhD, but still with the aim of teaching afterwards. When I finished my PhD, I applied for teaching, but I was offered a postdoc, and so I took that on, but always with the aim of teaching afterwards. So I don't think I ever stopped wanting to do that. I just ended up kind of going further and further into the research and into the academic career. But yeah, that was definitely my dream job.
In a way, you are living your dream, right?
Well, exactly. So, I mean, academia is a really great job, right? You get to do science, people pay you to do science, and I get to teach at the same time. So I think, yeah, I probably get the best of both worlds now. But I do like little kids. I used to teach a lot of little kids at gymnastics as well. So I always had that kind of idea of really early years. So probably past that now, though.
Yeah. In an imaginary world, what's your job? If you could pick another job, what would be?
I think if this imaginary world was a place where I was a little bit better at things, so maybe if I had a little bit more confidence, maybe a little bit more leadership skills, I think something I've always thought I would be interested to do, but would never ever really do it, would be to kind of look at education policy and science policy. So to think about kind of more advising government on science policy, to think about schools and universities and how the science curriculum is mapped out. That's something I would like to do because it kind of combines the science and the education, but probably not something in this world that I would ever have the confidence to go for, I don't think. So as long as I'm better in this imaginary world, maybe that.
Do you have any regrets in your life, in your career?
I don't think any big regrets. I don't think there's anything that would have changed my life and my career massively. I think I have lots of little regrets. I think I always regret I'm a little bit timid, I'm a little bit shy. I don't always have the confidence to do things quickly. And so I sometimes regret not taking opportunities a little bit earlier. Certainly not publishing papers and waiting for that absolutely confirmatory result and somebody else publishing it first. But no really big regrets. I guess I had an opportunity when I was a postdoc and an opportunity maybe 10 years ago to have a job abroad. And I turned those down for family reasons. And I maybe wonder a bit how things would have been different, just what would have happened, where I would have got to if I'd made different decisions, I guess, on those opportunities. But not so much a regret, just more maybe a wonder. I'm pretty happy with the decisions I made and the job I have, but maybe a wondering what it would have been like had I made different decisions. I think maybe my only regret at the moment is that I really don't get to see my family as much as I'd like. They live about 8 hours away from me now, and don't know what you know about UK travel, but it's not very easy. And so I'd like to see them a little bit more. We live at opposite ends of the country, which is perhaps the biggest regret of my current life.
If a time machine existed, would you wanted to go travel 100 years back or forward?
Oh, I would definitely go back. I think I would always go back. I really like history, so I think I would always want to see how things had happened. And actually, with my kind of recent interest in family history, I think I'd go back and meet my family. Maybe not 100 years, maybe 200 years if I get to cheat a little bit. Um, I really like to see what life was like for them, what challenges they had, how they ended up where they did, and how that's kind of really influenced the life that I've had and the opportunities that I've had. How did I end up where I was? So definitely backwards for many reasons, I think.
Okay, yeah, exactly. Just like me, I would like to go back to see what's happening in this world 100 years, 200 years ago.
Yeah.
So thank you, Professor. Thank you so much for your time. I enjoyed this conversation. I learned a lot, and have a great day.
Thank you very much for having me. Thank you.